Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element thallium. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Thallium is the 81st element in the periodic table. Its atomic number is 81 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. There were two discoverers of thallium, William Crookes and Claude-Auguste Lamy. They discovered thallium independently with the use of spectroscopy in 1861. Crookes published first, so he usually gets the credit. If you put thallium in a flame to vaporize it, don't do this, thallium is highly toxic, it glows brightly green in the flame. If you then look at the spectrum of the flame in a spectroscope, you see only one bright green color given off. From the Greek, thallos, meaning a green twig, Crookes gave it the name thallium. Both Crookes and Lamy produced thallium metal the next year in 1862. The major practical source of thallium are trace amounts found in copper, lead, zinc, and other heavy metal sulfide ores. Some of these are copper-bearing chalcopyrite, which, if treated properly, becomes the popular peacock ore, galena, or lead sulfide, and sphalerite, or zinc sulfide. Again, thallium is only found in trace amounts in these minerals and is therefore only a byproduct of copper, lead, and zinc production. Although production figures of thallium are withheld by the major producers, estimates are that in 2021, the world produced around 10,000 kilograms of thallium. From the information I can gather, this is a good order of magnitude estimate for yearly production in the past as well. 10,000 kilograms of thallium would be a cube, only 204 centimeters on a side. Let's throw an average person in there for comparison. China, Kazakhstan, and Russia are thought to be leading producers of this element. Thallium is a silvery, grayish metal when kept away from the air. In the air, it quickly corrodes to a dark gray. Currently, thallium is going for between $4,000 and $8,000 per kilogram. Surprising since it's not particularly rare, probably because it has few uses, as we'll see, and, as usual, prices depend on purity and quantity. Here's how the price of thallium has varied from 1942 to 2017 in inflation-adjusted $1998. Clearly, thallium would have been a good investment in 1980 if you wanted to store large quantities of toxic metal. The element thallium is pretty uncommon, coming in as the 71st most abundant element in the universe by mass, at only 5 parts per 10 billion. Twice as abundant in the Sun, it makes up 1 part per billion of its mass, and is the 58th most abundant element there. It's the 66th most abundant element in meteorites at 8 parts per 100 million. Not as common as I would expect, it's the 49th most common element in the crust of the Earth at 5.4 parts per 10 million. About the same as iodine, its neighbor to the right in this chart. Thallium is rarest in the oceans of the Earth, making up only 1 part per trillion, the 60th most abundant element there. Lastly, and like many of the elements in the upper reaches of the periodic table, there's no free thallium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Thallium is here. I understand this looks complicated, but let's look at just thallium a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of thallium created by various processes relative to the Sun. About 77% of thallium present today is believed to be produced by dying low-mass stars, the magenta area. The rest is produced in supernovae, the yellow area. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 81 protons for thallium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 37 known isotopes of thallium, and of these 37, there are 2 stable, non-radioactive isotopes, thallium-203 and thallium-205. These thallium isotopes occur in nature in the amounts you see here, most of which is thallium-205. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of thallium occupy the same place in the periodic table. Of the radioactive isotopes of thallium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest thallium half-life is thallium-204, with a half-life of only 3.78 years. These half-lives, compared to the 13.8 billion year age of the universe, are not even a blink of an eye. That's why we don't see any of these isotopes out wandering around in nature. They've all decayed away. If you want to experiment with these, they must be manufactured in a reactor. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of dividing by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice that there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Thallium has a fairly high density at 11.85 grams per cubic centimeter. As a reminder, water has a density of only 1 gram per cubic centimeter. I've put up more densities for you here. You can see thallium has about the same density as lead, and we all consider lead as being a pretty dense element. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, thallium's density is 11.85 grams per cubic centimeter, the magenta circle. It's about the same as lead, just a bit more. If I had one, this would be my most toxic block and would cost about $18,000, so maybe not. Thallium has a very low melting temperature of only 304 degrees Celsius. It has the 28th lowest melting point, and 12 of those 28 melt below room temperature. You could easily melt this stuff on your stove if you weren't worried about killing your entire family. Thallium boils at a fairly low 1,473 degrees Celsius or 2,683 degrees Fahrenheit, giving it the 63rd highest boiling point, or the 31st lowest boiling point of all the elements. That's less than 1,169 degrees Celsius above its melting point, giving it the 57th largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is that of neptunium, with a 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid in only a 2.51 degrees Celsius range. Again, thallium has the 31st narrowest liquid temperature range at 1,169 degrees Celsius. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. If we compare the size of the thallium atom to that of hydrogen, we'd see something like this. The thallium atom is about 3 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are profoundly small. Looking at all the element sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. Thallium has the 46th largest size atom of the elements, about in the middle of the pack. Thallium has a pretty high thermal expansion rate. As a matter of fact, it has the 8th highest rate of all the elements, a whopping 3 parts per 100,000 per Celsius degree. This means if I had a 1 meter long bar of thallium and heated it by only 1 degree Celsius, it would get longer by 3/100ths of a millimeter. That's about a hair width, and that's only heating it by a measly 1 degree Celsius. Thallium expands about the same as zinc and 30% more than aluminum. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. Thallium has the simplest spectrum we've yet seen, almost boring. It gives off only one single color of green light, as we saw in one of the very early slides in this presentation. Remember, this is the visible spectrum only. There may be other spectral lines in the infrared and ultraviolet we can't see. This spectrum uniquely identifies the element as thallium to scientists. No other element gives off this set of colors. Let's take a look at a few applications of thallium. There aren't many. This is a scintillation counter used to detect and measure the presence and energy of X-rays and gamma rays. Under the cap at the top is a crystal of sodium iodide. The interesting thing about this crystal is that when it's hit by a gamma ray or an X-ray, it gives off a tiny flash of light, and the brightness of that flash is proportional to the energy of the X-ray or gamma ray. It also glows under ultraviolet light. The crystal has a small amount of thallium added to it to enhance its glow. This is called doping. The flash is exceedingly dim. So dim, you must detect it with an ultra-sensitive device like this photomultiplier tube. The sodium iodide crystal is mounted directly to the light-sensitive end of the photomultiplier. When a light pulse from the sodium iodide crystal hits the photomultiplier, it delivers a series of electrical pulses which are then counted and have their strength measured. If you could listen to these pulses, they would sound like this. This visual representation has time running along the horizontal axis. The height of each pulse gives you the energy of the X-ray or gamma ray that caused it. If we measure the energy of each pulse and keep track of how many of each energy, we could build a histogram like the one you see here. Low energy on the left to high energy on the right of the horizontal axis, and the count of each specific energy detection on the vertical axis. The positions of the peaks you see are unique to the radioactive substance you're measuring, allowing you to identify the specific isotope, in this case, cesium-137. Gamma-ray spectroscopy is an extremely useful tool, and thallium is an important part of this. Similar to the sodium iodide scintillator is this cesium iodide scintillator. Same idea. In both cases, the tiny bit of added thallium enhances the amount of light given off when hit by gamma rays, making lower energy radiation easier to detect and count. Small amounts of radioactive thallium-201 compounds injected into the body can be used in gamma-ray imaging. Thallium looks useful in evaluating coronary artery disease, or, in this case, distinguish less harmful toxoplasmosis from primary central nervous system lymphoma in the brain of an AIDS patient. This test can speed proper treatment with a quick diagnosis. The use of thallium radioisotopes have largely been replaced with technetium isotopes. These thallium bromoiodide windows are specialized glasses containing thallium. They're used because of their infrared transmitting qualities. This is a prism made from thallium-containing glass. It has a high index of refraction, meaning it has a stronger light-bending power. Thallium, in the form of thallium sulfate, was used as a poison for rodents and insects. I'm not sure I'd want to use it to kill bed bugs as advertised and then have to sleep in the same bed as the thallium poison, however. It was banned for home use as recently as 1965 and banned commercially in 1975. In the late 1800s, thallium sulfate was used to treat syphilis, gonorrhea, and gout, but the side effects were severe, and this treatment was not widely used. This is undoubtedly an example where the treatment was worse than the disease. In humans, it kills at doses of only 10 to 15 milligrams per kilogram of body weight. Thallium is known as a poison of choice for committing murder. Indeed, thallium salts have been called inheritance powder. None other than Saddam Hussein used thallium on dissidents before allowing them to emigrate and die after they left Iraq. Agatha Christie used thallium as a poison in her 1961 novel, The Pale Horse. She described the symptoms accurately enough for fans, who happen to be nurses, to recognize those symptoms in real people and notify doctors who were unaware of thallium poisoning. This may be the only example where the fictional use of thallium as a poison saved real-life victims from a terrible fate. If you are poisoned with thallium or its compounds, one treatment is to take large amounts, up to 20 grams per day, of the pigment Prussian blue. It absorbs thallium and it exits the body in the stool. Probably gives your stool a lovely blue tinge. Prussian blue is more familiar as a pigment used in painting. You are probably familiar with the famous The Great Wave of Kanazawa by artist Hokusai, where he makes masterful use of Prussian blue. Aside from fever, gastrointestinal problems, delirium, convulsions, and coma, one of the effects of acute thallium poisoning is hair loss. Marketers never wanting to miss an opportunity to turn lemons into lemonade, sold a thallium cream as a depilatory. Corumlu cream, the word of magic in removing hair, a new hair cream guaranteed to devitalize superfluous hair on any part of the face or body. A cream, too, that does not in any way harm the skin tissue. A jar is worth much more than its price of $5. I'm sure overuse of this cream would halt hair growth permanently and forever. May they rest in peace. Aren't you glad we have the FDA nowadays? It's hard to believe that any company would be clueless enough to name a perfume Thallium. It's a killer scent. Something I'll bet Agatha Christie wished she'd thought of. Your body contains no thallium, and it serves no essential biological purpose. As I've stressed, thallium is highly poisonous, and the use of its compounds, like rat poison, have been outlawed in almost all countries. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about thallium. As a sulfate salt, handy for killing rodents or one's relatives. In the next program in this series, I'll examine another somewhat toxic element, lead. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element thallium.